is Mr. Scott Arnold, who's the Director of Engineering Solutions at Fyfe Company. He has been working with Fyfe Company for 24 years on the design and development of the Typho Fiber Wrap Advanced Composite Strengthening System. He is a licensed civil engineer in multiple states and has a Bachelor of Science in Structural Engineering from the University of California at San Diego. And good to know. And he will be speaking today about FRP design, methodology and applications for blast and impact resistant structures, a manufacturer's perspective.
I'd like to thank Mark and Cares in any case for inviting me to do this. It's a nice opportunity. You'll recognize some of the pictures as I listened to some of the other talks. I started thinking, oh, all these other slides I could have put in here. That'd be so much better. But anyways, got to work with what I can here. So I would like to emphasize that, yes, it's an engineering perspective. I've been involved for almost 25 years, right out of college, UC San Diego, into the test laboratory, where test labs are actually my favorite thing in the world to do. If I could pay my mortgage, that's where I'd be working, because it's awesome. But immediately got into the testing with, happened to be at Fyfe at the lab at UC San Diego. It was all based on seismic. It was all focusing on seismic bridge work. And that's expanded, and obviously I want to stay on topic with the blast. But what I see is there's a lot that combine. It doesn't really matter whether you're talking about a seismic event or a blast. How this gets into the real world and gets applied and people get paid, there's a lot more to it than what just happens with an academic approach. So I'm not going to preach to the choir. Seismic is quite a bit different than blast. Looking at that, my job is not to be an expert, which is so awesome. I get to have you be the expert in this. All I need to know is what my materials do. What I've found over the years is that there's a fundamental misunderstanding still to this day of what the materials are. People have moved past and started talking about how to design them for shear and flexure and call them confinement, and I can talk about that till I'm blue in the face. But at the end of the day, there's still a real misunderstanding of what these materials are and how they behave with reinforced concrete or wood or steel or anything for that matter. So as we've worked through the field of blast, we've dealt with all of these types of things, and what happens here is I have sometimes academia, but usually it's a consulting engineering firm, ring us up and ask, will this material provide a solution to my structural problem? And we have to talk about that. We have to talk about what exactly is the structural problem. Talk about what are your alternates. At the end of the day, this industry doesn't exist unless you save people time and money. So I have to be able to show to people, first, that we can solve the structural problem, and then second, that it's going to save them time and money compared to what they would have done, because there's more than one way to skin a cat. And at the end of the day, that's the name of the game. It's saving time and money. It's not research, no offense. It's not that. It's saving people time and money. So I have to take what's done in the laboratory and find practical purposes and bring those solutions to these clients who have owners that have to save time and money. By the way, I'm not going to read to people. It's just something I don't do. So what I want to do is show just a quick comparison. This is actually just a comparative, it's a shake table test. Do that. There we go. Perfect. This test done a while ago, and it's very dramatic what these materials can do to a structure. And showing that to people get really excited. This is an unreinforced, ungrouted CMU block wall with a mast that, thank God, is hooked to an overhead crane above. Otherwise, it's been a real problem on the shake table. And then what you have next to it is the exact same excitation event being hit on the table. And all we have here is one layer of glass. It doesn't even cover the entire face of the wall. And then we have glass anchors going into the foundation. Still, just a remarkable difference in the performance, and for very little cost. For most of the time with blast, we've seen that these glass systems will tend to outperform the carbon system. Again, a lot of this you've probably already seen. This is a test we did with Baker Wrist back in the day. And the glass is on here. I get a lot of confusion with that. You can see the grout lines behind the glass material. Glass is somewhat translucent when you saturate it, and anyways, it's there. You just got to trust me. It's 2 layers or unidirectional glass. It's just spanning vertically, simply supported at the top and the bottom. And what you don't want to do is catch all that load and shove all that load right into your connections. And the stiffer element you put on that wall, the more you'll do that. So by using the glass and using that 2% ultimate elongation, you can actually spread more of the plasticity through the member and send less of that load to the joints. And you don't want your joints to fail. It's a very bad day, as Zach was referencing on that. When we had done some of these tests, we played with different amounts of coverage. I don't know if I can get this to work. So if you don't cover the whole wall, there's a danger of small pieces flying out and hitting somebody. So although you may save some money by not covering the entire surface of the tension face of the wall, obviously you want to prevent small pieces from flying and hitting people. So we tended to go with the full coverage. I just thought I'd show you that. Before I get into this, because polyuria has quite a bit higher elongation, it's not FRP, also wouldn't suggest using it. I want to talk about elongation. We use glass sometimes in blast events because its ultimate elongation is roughly 2%. By the way, that's true of everyone's glass, everybody's products. You should consider GFRP as ultimate of roughly 2%. It'll fracture. Same is true of carbon, except it's roughly 1%. So everyone's carbon, I don't care whose it is, product X, Y, and Z, 1% is the ultimate elongation. I see this, a lot of confusion. There's people that talk about 1.8, getting close to 2%. They're talking about the dry fabric. You cannot do that with this material. Aerospace knows it, and yet we're screwing around with this all the time. I see confusion all the time. When I talk about not understanding the materials, I'm talking about people usually somewhere between dry properties, like 33,000 KSI modules. Okay, that's not this. That's not what's out there doing the work. That's this. All right? Close to 2% module, or 2% elongation. That's not this. That's not what's out in the field. That's this. And oh, by the way, your concrete and steel is trashed when you're getting that high anyway. So you got to. So when I talk to engineers, it's how do you design FRP going into the world? I don't care whether it's blast, a seismic event, whatever it is. It's strain compatibility. That's what it is. You need to know strain compatibility with the reinforced concrete, the wood, the steel, whatever it is, the masonry, whatever it is you're putting it on and working with. You have to understand that. And if you think this material has close to 2% elongation, you're wrong. That's a carbon system, it's 1%. And people mess around with this all the time because you can tweak the equations that spit out results when you follow some of these guidelines that have been created. I'm not a huge fan because the guidelines have to improve. Polyuria sounded good, very high elongation, pretty awesome stuff. You can put it on walls, and looks great. Right up until you try and install it. You realize about 20 to 25% debonding should be expected with almost all polyuria applications. 20 to 25% of the area you should go ahead and assume you didn't install it right, didn't debond, or didn't bond properly to the substrate. And it's hard to get it on right. It's hard to get on the right thickness. It drips. It's really hard to control. And then we kept getting these questions about fire. So we went ahead and did an E84 test, and we almost blew up the lab. Yeah, it turns out polyuria at the right temperature is the opposite of safe. So I don't suggest it. We don't sell it anymore. Saw this slide earlier. I just like tyforce method because when people start talking about tyforce method, the retrofit looks exactly the same. It's super simple. I like it. When can you use it? When can you not use it? That's on you. I don't care. It's the UFC. Study it. What I want from the designer, I need a design engineer to be very clear about two things: the capacity of the element and the new load demand, and the dimensions of it. You're liable, as the engineer of record, you are liable for those things. The capacity of that thing, the new demand from whatever it was, the blast event, and the geometry of it, that's all on you. At the end of the day, we at Fyfe and through our applicators, our certified applicators, we are then liable to pick up the difference, which we help them clearly define on the bid documents. What I don't like, again, is this through this misunderstanding, fundamentally, I think, of the materials to start with, and then how they're used, I see bid documents at the streets that are very apples and oranges. And my job over the 25 some odd years has been basically trying to get these bid documents to be apples to apples. I think all of us as engineers would agree that when it hits the streets, it should just be apples to apples. And getting that to be true, very difficult. I want 50 kips of tension in that element and design it for ACI 440. Okay, that's apples and oranges. It's apples and oranges. It's not the same. And I can show you the gray areas, but it takes a little time. You've seen some of these. Sarah, thank you for the work. This was actually originally with UT Austin, I think, we started, and then In-Sung Kim picked it up, and Wasim Gonam picked it up, and I don't know if Jim Years is around here. I saw him, but he was retiring, so I don't think he came out. But early on, working at UT Austin, we learned a lot. In practice, this is one of the projects we did. It's a Cake Courthouse out in Oahu, and the problem here is discontinuous top steel in the slab, basically, and we're just creating that continuity. But what we see here, and from Dr. Orton's early testing, was when you have discontinuity, whether it's in your bottom steel or in some cases in your top steel, and creating that continuity through the use of these materials can be doable. What we find is the geometry is a pain in the butt. You see here, it's a small scale specimen, and we're drilling through and we're sending anchors through. Very tricky, the geometry of how that joint is formed in the road and getting to it and getting access and really making this work can be quite complex. And quite honestly, a lot of times when we've seen things like this, we've had to suggest they take a different method, use reinforced concrete or steel or something else. You have to make sure that the mechanics work. This is the top one here.
Pop for a while.
I don't know if Austin showed this yesterday. I wasn't able to make his talk. This is at UT Austin. Very interesting testing that was done. If you bond three-sided to a beam for shear, the mode of failure will be debonding. The question is, when does it debond? So you grab your 440, you go through your K factors, you figure out what the debond stress is going to be. All right, I'll ask you this. Did they prep the concrete the same there as they did there? Is the concrete property the same there as it is there? Have you ever been to Quebec and seen the concrete? How confident are you in that debonding strain that you empirically came up with? All right, that will almost always govern what this can do. However, this did not fail by debonding. So look a little closer. This failed at ultimate. The carbon's fractured. What actually happened was when you read the dilation strains and you've got a load there, I wish I had my laser and the support there. What actually happened is you get a dilation strain of roughly 0.004, 0.005, 0.006, and that shear crack gets just wide enough that you lose your aggregate interlock. You lose your V sub C component, and it goes from 0.006, boom, to 0.1, and bam, it breaks, and boom, it debonds very fast. So really, I would argue the ultimate here to design would be about 0.006 based on the crack width, essentially, and that's true of columns as well. How you get it to this is by anchoring it. Fully anchoring that strip. So what's fully anchored? What's the embedment depth? What's the spacing? What type of anchor? This is all the stuff that we've spent a lot of time working on testing. If you look at the gray, that's the control, the red is the anchored. If you follow the guidelines by the ACI committees, that dot should be up closer to 120, but it's not. It's not there. It's lower than what you would expect with our current guidelines. However, you add the anchors and we're well over it. This here, I think I can show that as well. Pretty interesting. That ash toe girder is just pretty big. It's almost as tall as I am. It's hard to see, but you see the load there and again the support there. We've got anchors at the re-entering corners and some in the field as well. Some of the guidance being given on these is, again, not great in terms of what the current guidelines show. Again, this is more seismic, but it has everything to do with detailing in the real world for a blast as well. These are, again, all very much related. What I can tell you is through this testing, I can now remove debonding as a mode of failure. If I'm allowed to design it the way we want, based on the testing that we've done, debonding will not be your governing mode of failure. We can literally remove it. This was completely debonded on purpose. The only thing we had is a three-sided and then fully anchored, and we actually performed much better than I expected. I would still, by the way, suggest that you can treat it as a bond-critical application and still bond it, but we wanted, this is fun to do in a lab, completely debond it. I wouldn't necessarily suggest that at this point in time in the real world. But we did prove, in fact, that you can take debonding out as your governing strain, as long as you detail it correctly. And that's a longer conversation. You can improve the performance of walls. We did quite a bit more wall testing with and without anchors. The detail you see there with the beam is more or less what we tested at UT Austin. By the way, whether you go straight in or whether you angle 6 for one, half dozen for the other, but in terms of where you drill the hole, you can't drill the hole all the way up against the soffit if you go straight in because of the dimensions of a drill. You're going to end up 1.5 inches or 2 inches below the soffit because of the drill. But if you slightly angle that, you can get the hole right up at the top, closer to the compression zone. I'm trying to get my tension member up into the compression zone. It's very similar to steels and ties and what we already learned about, right? And this can substantially improve. And basically, you can start designing these, if you can justify it through your tests and what you've done, the same way you would design a fully confined column. We've also run anchors right through the slab and all the way around and done some different details with that. This is one of the tests that we've done. Notice we are using glass. It's kind of neither here nor there. But the idea, and I get the question a lot, when do you use glass and when do you use carbon? You need to achieve a performance goal, and you need to do it at the least possible cost. Right? So it gets back to when to use glass and when to use carbon. Check it. Run the numbers for both. Go to your contractor. Talk about it. Figure out what's involved. And guess what? The glass might actually be less expensive, and you might not need carbon. This is an example of that. I just want to show you how our anchors are installed. There's some differences in this concept, but again, the hole is drilled as high up as you can. We fill it half of the way with thickened epoxy. We take the pre-saturated anchor here, push it into the hole, fan it out, take that same thickened epoxy, butter it up, is what I like to say, and then take a second layer and sandwich it. So the anchor is actually between the two layers of glass there. This worked very, very well. We've done it on multiple tests. Yeah, what can I say? Oh, by the way, just so you don't not confuse, the red there, those are just thread rods on the test specimen. I get a question on that every now and then. It's just thread rods sticking out of the test specimen. We just taped it with red duct tape to keep the epoxy out of the threads, just because you don't want epoxies in your threads. So that's what those are. And again, they've already prepped the surface and they've already primed the surface. That's why that looks wet. It's just wet with the primer epoxy is all. So we've done a lot of different tests. We've used this for a lot of different reasons. Confinement of boundary elements, just tension going through obstacles. More often than not, these will be carbon when you're quantifying the tension force you want to transfer through something or into something like embedded. More often than not, we're going to go with a carbon anchor. If you're improving the detailing at, say, termination points, we'll often then go to a glass anchor. It's a lower modulus, can actually be better while it's working with concrete. Here's some pictures that probably everybody and their brothers use. This is from out in White Sands in early days, working with back and forth with UCSD and others, playing with large bombs. But you've already seen a lot of on columns, no sense to repeat it. You get the idea. At the end of the day, we want the event to come and go and the column to be able to take its axial load so people can walk out of the building. I mean, that's it. You might need a new building. But at the end of the day, as structural engineers, right, I want to be able to take these events and sustain life. But you got to expect there will be failure. I think the best thing we can do as engineers is control where it fails and how it fails, and at what displacement. So this is some work done by Karazogian and Case. Pretty cool stuff, pretty cool pictures. I'm not a huge fan of FEA because it's pretty cool pictures. Great to sell to clients. Works awesome. It's pretty impressive. But if you don't correlate it with actual testing, I have a lot of holes to punch in it. Don't get me wrong. It's a valuable tool. When repeated, I've seen it, so it is a valuable tool. But there's a reason we do structural testing. If it was as great as a lot of people think it is, we wouldn't have structures labs. But the reality is you've got to correlate that with real tests. So this was done. Zach showed a little bit of it. He was intimately involved in this project. As we zoom in, I liked, Zach, your slide talking about the different overlaps and butt splices. A butt splice here, an overlap here, how far of an overlap. How well do you detail the seams and edges? I remember after this test, one kind of just observation that had we put more thickened epoxy, it seemed, just over all of the exposed surfaces, right? I think we got another picture here. Oh, look at that guy. Look at that guy. Anyway, I was going to give you a sunburn joke, but I'm going to move on. Hold on, let me play this. It's stuff that some of you may have already seen again, but this is a close-in blast test. Specimens way over there. There's a bomb, and there's a specimen. So pretty cool. I actually didn't think it was going to work. I was a pessimist. I didn't think it was going to work at all. When we looked at it, and this we were observing that, oh my gosh, in the areas where we had, because we always, it's really important for every single project to provide shop drawings. What I explained to our engineers, like when our contractors call us up and we've looked at with the bid documents and won the bid and great, we always send out shop drawings. I'm never going to have a crew working off of the actual bid documents that were originally made because they never have all the details you need. Where are the butt splices? Where are the overlaps? How do you deal with the corners? How do you finish it? Two biggest things: surface prep and finish. Surface prep and finish. It's bond critical. You've got to get all the way to your substrate. You can't have non-structural coatings. A lot of people want to have non-structural coatings and bond to it. Trust me, it's not what you want to do. We've seen enough in our testing to know for bond critical applications, it's just that. Surface prep is your number one thing, and your second one is going to be anchorage. And then again, don't forget finish. Don't forget finish. In this one, had we put that thickened epoxy not just at the seams and edges, but over all exposed faces, it actually would have done a lot better. And we saw that. I don't have a great picture but as you were showing here, it was like, oh yeah, I remember that. So a detailing thing for close-in blast, I would say, hey, hit all exposed surfaces with a layer of the thickened epoxy, and then come up and put your pretty cladding or whatever it is. But make no mistake, I say pretty cladding, it sounds kind of quip, but the architects carry the ear of the owner, and you will have to deal with how this looks. And as I say, surface prep and finish, don't forget finish. It makes a huge difference. Who's going to be touching this? The public. How close do they get to it? What's it going to look like? As an embassy in a very volatile part of the world, I hear they're going to move the embassy. That's about all I can say about that. There's Zach again. Look at that. You got shorter. That's good. Sorry. Anyway, this is again working with Baker Risk. We worked on basically a macho curtain wall. I don't know how else to say that. It's a prefabricated curtain wall. We designed it specifically to take certain blast loads. I didn't want to put all of my videos and things in here, but it's a little bit heavier, but it combines a little bit more concrete on the compression side and a lot more tension on the tension side. And at the end of the day, we've done a whopping one project. This is an air traffic control tower that we worked on. These are the panels getting installed. Again, new construction. New construction and fiber reinforced polymers is in its infancy. To some degree, retrofit and repair. I mean, here I am over 20 years into this. Had you asked me 20 years ago, where would this industry be? I would say every engineer would be designing it comfortably, every contractor will be installing it comfortably. We're not there. We're nowhere near there. It's still very much specialized. I see a lot of confusion in the industry. And again, a lot of, just before people start jumping into their equations, they're literally confused with the material itself. And I've seen this from all walks of people in the industry. There's a lot that we learn from trial and error. There's a lot we learn in the laboratory. There's a lot that's learned in the field. And I just can't express enough how important it is to try and pull all that together. Take very seriously what the contractors in the field are telling you. Take very seriously what the people in the laboratory are telling you. But you need to be able to merge that. And over the years, I've found it's a very tricky thing. Although I think this is a great product, I don't see it being used that much because I see everything it takes to get it to market. Right? You have to come on really, really early stages with an engineer to talk about how they're designing their steel moment frames before this will even happen. Because you could use precast, there's other ways you can build this structure. It's clever, it's cool, it gives you a little more floor space and stuff, but it takes a lot of work. So our focus has been really just zeroing in on the manufacturing of the product in a consistent fashion. Going from a mom and pop company, as it were, to a corporate America. There's some pros and cons with each. I've learned mom and pop very, very well, I think. Now we're in a corporate environment. AGEON's a billion-dollar company, and what I like about it is that I no longer have to even think about quality control. As we expand and grow, I don't have to worry about it. I really worried about it a lot when we were a mom and pop company, but I no longer have to worry about it. We're ISO controlled, it has to be transparent, we have stockholders to answer to, and that is handled. There's whole departments to deal with it. So I can focus on what I like to do, which is talk about people's unique problems and see if this can be a solution for them. Again, working through the years and working with various professors, I would welcome your comments and input and questions because as I mentioned, I think where the rubber meets the road is testing it and proving it. And over the years, the hardest two things I've had to deal with are predict its performance, prove that you can predict its performance. Don't throw me a booklet or a guideline or a code, prove it. And the next one is how long is it going to last? Right? And this is a big one. Hardest question I ever got, what's your warranty? And I usually just for fun like to ask the group, do y'all know what warranty you get from your steel suppliers? Anybody? Anybody get a warranty from your concrete suppliers? You design it for 50 to 100 years. This is not a coating. This is not a waterproofing membrane. It's a structural member. It comes with all the liability of steel. You cannot get a 20-year warranty. This is a really, I don't know why it's confusing. You can't do it. You can't get it from your steel supplier, your concrete supplier, and you can't get it from an FRP. And if you get some weird warranty kit, it's probably worth the paper it's written on. At the end of the day, this comes with all the liability as those structural members, and you have to design with the assumption that it'll last 50 to 100 years, just like you do with steel and concrete. All right? So I strongly suggest solid testing. I strongly suggest a lot of trial and error and background and understanding who has the liabilities, because at the end of the day, these are, we are engineers, and there's a lot of liability involved in this. So again, I know there are some other things I wanted to talk about, but any questions? No.
No question?
Yes, sir.
So based on your presentation, what do you think is the best approach to designing FRP retrofits to existing structure for glass or other applications? Do you think that the engineer would start with the concept and then maybe consult with the manufacturer to get like
great
a
question.
concept approval, or is it like a pre-discussion, pre-concept thing? You discuss with the manufacturer, say what alternatives can I do? What do you recommend? And then
Yeah, a little bit of everything. Good. So good question. How does this proceed, right? So the more savvy an engineer is about the use of fiber reinforced polymers, the easier my job is. However, I do strongly suggest, when considering the material, to be very, very clear first about what exactly is there and what exactly are you trying to do with it. I see a lot of people punting this one. Going, I need 50 pounds per square foot. Really? Like, what is the real capacity? I wasn't sure, and I bumped it up, and I pushed that down, and I want 50. All right, no. You gotta have to do, and I see this a lot. I just say it jokingly, but I see it a lot where they think there's some kind of magic. I don't know if it's shiny or something. It's not magic. We need to know very specifically that capacity, that demand, but normally that would be a conversation of the engineer. And choose your manufacturer. I mean, I'm happy to help. There are others. Buyer beware, but you gotta prove it at the end of the day. So having that conversation, but don't take people's words. Show me some examples. Show me that proof. Show me the testing. Where is it relevant? Why is it not relevant? How is it going to save me money? My question to you or to the engineer will often be, what are your other options? Because I want to know. Quite honestly, I'm interested. And we'll have a very frank conversation about that, and then pulling in a contractor to get a very real estimate of what this is going to cost. And this is, you got to be very careful with this. People talk about square footage. And what is exactly that are you including removal and replacement? Is there hazardous abatement? Did you include fire-resistant coatings? Do we need fire-resistant coatings? What are we going to do with the authority having jurisdiction? I forgot to mention, Brian Gerber's in here. You got to pull a permit. You could have the best thing since sliced bread, but if you cannot pull a permit, you're dead in the water. I've been dealing with bridge industries, building industries, nuclear industries, water industries. It's all different. And you have to be able to pull the permit. I've walked away with my tail between my legs. And then gone back $200,000 worth of testing later and come back. So at the end of the day, I think it needs to be a conversation between the people that can clearly define the structure and the structural issue, and the people that have a comfort level designing it and working together and just making it apples to apples. I don't even want you to sole source my stuff. I honestly don't. I just want it apples to apples. And understanding that might not be as easy as you think. Yes, sir.
Scott, do you have the ESR report for the Fyfe product?
Yes, sir, Bob. We were the first one ever on the planet to get one.
Code and everything like that.
I worked a lot with Brian Gerber, happens to be in the audience, when it was ICBO before it became ICC. When we first did this, it was all bridges, right? So it was just bridge construction and bridge columns, and we got our Caltrans approval. And then we actually got a City of LA research report because of the 1994 Northridge earthquake. And then we went and got an ICBO, now ICC, evaluation service report. And it's a great point, because if you start pulling products that say aren't approved for columns for shear, very common, probably my bread and butter, columns for shear. I see a lot of people with ESR numbers and they're not approved for columns for shear, but they're saving money. But as an engineer of record, if something goes wrong, and you designed with a material that was never tested and approved by the building code for that reason, I can tell you who holds the liability. It's not the manufacturer. It's the engineer of record. The manufacturer might pay a little bit to, whoop, I'm out. And your errors and emissions insurance are holding it.
Yes.
So it is important.
Yes, steel and concrete are covered in the ICC code, but this product is not covered, so you have to get
It is,
evaluation.
it is, but it's different. It's
Yeah.
not covered as well, I guess, is a simplified way. But we do have an evaluation service report. It talks about the environmental durability and then specific structural purposes that we've been tested by third parties and evaluated to be approved. So it's very comprehensive and time consuming, but it's a necessary evil. And again, the value to it, for years I didn't even understand the value to it until I started understanding liabilities. It also helps me a lot to prove two things. Can you predict its performance and how long is it going to last, which I can drill very deep into both of those. And the ICC testing and everything we did is a lot of it. Not everything though.
Well, thank you.
Sure.
All right, thank you very much.
All right, cheers.